Okay, so this lecture is on the hydrocarbons and specifically the impact of the hybridization state of carbon on the properties of the carbon-hydrogen bond and the carbon-carbon bonds of alkanes, alkenes, and alkynes. So I'll remind you that alkanes are compounds that have only carbon-carbon single bonds and carbon-hydrogen single bonds. And of course, this exception would be methane, which only has one carbon. On the other hand, alkenes have a carbon-carbon double bond, and then alkynes would have a carbon-carbon triple bond. Right? So the three classic families of hydrocarbons, at least of aliphatic hydrocarbons, these are not aromatic compounds, would be alkanes, alkenes, and alkynes. And I'm sure it did not escape any of your attentive views that the only difference here is the vowel, which changes from A to E to Y. Okay? I will point out here that alkenes are somewhat similar in terms of hybridization state to the aromatic hydrocarbons, which are called arenes, the simplest of which is benzene, right? And benzene is an arene. Okay? Now, what we're interested in is the CH bonds and the carbon-carbon bonds. But in particular, when I look at an alkane, since all the carbons are sp3 hybridized, then I'm looking at the bond between the sp3 hybridized carbon and the H, which is the s orbital, and the carbon-carbon bond between the sp3 hybridized orbital and the other sp3 hybridized orbitals. I'm looking at these two sigma bonds. In the case of the alkene, even though there may be carbon-carbon single bonds, which are sigma, we are looking in particular at this bond, at this system. Okay? We're looking at the bond that defines the alkene, which is the carbon-carbon double bond. And we'll also look at the CH sigma bond, where this carbon is sp2 hybridized. In a similar fashion, even though an alkyne might have carbon-carbon single bonds, and for that matter, carbon-carbon double bonds, we will focus our attention on what makes it an alkyne, which is the carbon-carbon triple bond, and the concomitant carbon-hydrogen single bond if the compound is a terminal alkyne. And what we want to look at, in particular, is the impact of the carbon's hybridization state on the characters of those bonds, namely the bond's length, the bond's strength, the bond polarity, and any consequences in isomerism, which is something we'll talk about later. And as a rule, much of what we describe for the alkenes would apply to the arenes, and we're going to kind of keep that, keep the discussion of the arenes kind of limited. We'll look at that more when we get into 302. So what we'll do is we'll set up a little table. We'll set up a little table, if this will work. Here we go. Here we go. And what we'll do is we'll probably look at, say, the family of the compound. In other words, alkane, alkene, alkyne. We will look at the hybridization state, right? Then we look at the carbon-carbon bond. We look at the bond's length. We look at the bond's strength. And we look at any isomerism that might arise. Okay? So I'll move this over a little bit to sort of centralize it. So the carbon-carbon system. Then we'll also look at the carbon-hydrogen bond. And we look at the bond's length, the bond's strength, and now the bond's polarity. Okay? And as we see in a second, the bond's polarity will affect the bond's acidity. Well, so the families we're looking at are, again, the alkanes. And we are looking now at the carbon-carbon bond that we mentioned earlier. This is sp3. This is S, and this is sp3. So we're looking at the carbon-carbon bonds and the carbon-hydrogen bonds. So this is sp3. we're going to look at the alkenes, and we are going to look in particular at the, oops, I'll need to move that. We're going to look in particular at this scenario, which is these carbons are sp2 and sp2, and of course this H is S, and of course then at the alkyne, and we're looking at the this is S, sp, sp, and we're looking at the sigma bonds, at the triple bond and the C8 sigma bond. So the hybridization state of the carbons that define alkanes, again, are sp3, which have 25% S and 75% P. sp2, which have 33 1/3% S and 66 and 2/7%, 2/3%, P. And then at the sp, which are 50% S and 50% P. So let's talk about the bond length. Well, you remember, and this is the carbon-carbon bond, you'll remember that we said that the more S character that a, let's go down one. Come on. Well, I guess we can do it here. So you remember that we said that if I have a carbon that is sp3 hybridized, it's going to have significant P character. So it's going to look something like this. That would be sp3. And then just remind you, sp2 would be somewhat shorter and rounder, right? And then sp would be smaller still and rounder still. So that's sp3, right? That's sp3. Oh, crikey. That's sp3, sp2, and sp, right? And so the length of the carbon's orbital is changing. So this is not surprising then that if I link two carbons that are both sp3 hybridized, then the bond length, the internuclear separation, is going to be large. On the other hand, if I link two carbons that are sp2 hybridized, right, then the sigma bond I would expect to be relatively small, and it would be even smaller still, or shorter still, if I had two sp hybridized carbons. So just from that perspective alone, I would expect that the bond length, right, the bond length would rise in the direction sp, sp2, sp3, right? So the sigma bond in the alkyne should be the shortest because it has most S character, so it's the smallest. And the sigma bond in the alkane should be the longest because it has most P character, right? There's 75% P character. But it's a little more complicated than that. Because if you remember, the alkane only has a carbon-carbon single bond. So there are only two electrons in the, there are only two electrons in the internuclear gap in the alkane. In the alkene, in addition to having a shorter sigma bond, because the carbons are sp2 hybridized, you now have 4 electrons in the internuclear gap. And you remember that the force of attraction between charged particles depends inversely upon the square of the distance apart. And that depends upon the charges Q plus and Q minus. So as I raise the amount of electrons in the internuclear gap, as Q minus goes up, right, the charge goes up, the force of attraction goes up, and as the force of attraction goes up, the distance between the particles drops precipitously. So I would then say that the carbon-carbon double bond is much shorter than the carbon-carbon single bond for 2 reasons. One, the sigma bond is shorter. And 2, because there are more electrons in the internuclear gap, then the 2 atoms are pulled closer together because the force of attraction is greater, and that also adds to the bond being shorter. You might expect then that for the case for the alkynes, that this would be even more, because the sigma bond would be shorter, because I'm dealing with 2 orbitals that have 50% S character, so they're very, very small. So the sigma bond is shorter, but now I also have 6 electrons in the internuclear gap, and as a result, the force of attraction between those nuclei would have gone up, the nuclei would have become closer together, the bond length would have contracted. So for those reasons, then, I can actually say that in terms of length, the sp3, the bond is the longest in alkanes, it is intermediate in alkenes, and it is the shortest in alkynes. Well, we know how the story goes, right? Because if the bond is short, right? If the bond is short, if R is small, then the force of attraction is large. So I would expect then that the strongest bond would be the triple bond. This would be strongest. This would be intermediate, and this would be the weakest bond. Okay? Now, I could use the same arguments we used earlier. I would say that the triple bond is stronger than the single bond, for example, because I am dealing with carbons that are sp hybridized, and therefore the sigma bond they form is going to be short and strong. But I also have more electrons in the internuclear gap, and that's going to result in greater force of attraction. And all a bond is the force of attraction. So if the attraction has gone up, then the bond strength would have gone up. But I can link the greater strength of the triple bond to both the character of the carbon, the hybridization character, and the amount of electron density in the internuclear gap. Well, what about isomerism? So we have defined isomerism before as the existence of more than one compound that has the same molecular formula. And so the isomers we've seen before would include things like, say, dimethyl ether versus ethanol, right? These are both compounds of formula C2H6O, and these differ only in connectivity. Well, it turns out that if I look at alkanes, I can get different kinds of isomers which actually happen to have the same connectivity. So these are isomers that have different connectivities, and so I call these constitutional isomers. Right? These are constitutional isomers. Where did this go? If I look at an alkane, why is this being difficult? If I look at an alkane, down, 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 good Lord. If I look at an alkane, so down, oh, crikey. Okay, let's see if I can get this to work. Down, 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 heck, down, there we go, new page. Right, right, those are constitutional isomers. With alkanes, on the other hand, an interesting situation arises. So, for example, let's imagine ethane. So I can draw ethane like this. And ethane, of course, is C2H6. So I put an H here, and because both carbons are tetrahedral. Well, if I put my eye, well, that's a bad place to put my eye. If I put my eye and I look at ethane from here, what I will see is the following. I'll see a triangle that has this H here. This H would be to my left, and this H would be to my right. So if I label them H, H prime, and H double prime, I'll have H, H prime, and H double prime. But in the back, I actually won't see this H at all. It'll be bang smack behind this one, right? So what I'm going to do is I'm going to draw a circle that will represent the back carbon, if you will. But I really won't be able to see these H's. So if I call these H's, let's call it H, HA, HB, and HC, then from my perspective, HA would be bang smack behind H, HB will be bang smack behind H prime, and HC will be bang smack behind H double prime. But I can rotate about a single bond. And suppose I rotate that a little bit, just about 120 degrees. Then what's going to happen is I'll get this arrangement. Okay, and we're going to come back to these things and deal with them in a bit more formal fashion in a little bit. But if I keep the front carbon stationary, they will remain like this. But the back carbon now ends up looking like this if I rotate through 120 degrees. So what's going to happen is if I rotate 120 degrees going into the board, HA is now going to be here. Right? So in fact, let me draw it another way. So if I rotate 120 degrees, keeping the prime stationary, what I'll get will be H here, H double prime will be here, and this H prime will be here. What I will get on this carbon, oh crikey, what I'll get in this carbon will be HB would have come in the plane of the board, HA would have rotated behind the board, and HC would have come up and in front of the board. Right? So I'm just going 120 degrees. I'm bringing HC from the bottom to the top. HA would rotate back into the board, and HB would rotate forward into the plane. So when I look at this structure now, I'm going to see HC on my left, on my right. Right, so my eye is still in this position, right? I haven't changed my eye. HC will be on my right, HA will be on my left, and HB will be at the bottom. Okay? Now, so now I can see all 6 hydrogens, which I couldn't see here before. These two structures have exactly the same constitution, right? I've got a methyl attached to a methyl in both cases. So they're not constitutional isomers, but they're isomers nonetheless. And they're isomers because they're not entirely the same structure. And in fact, a really good way of looking at it is if, for example, I had changed these H's to, for example, chlorines. So let's say I made these, oh, crikey. Let's say I made these H's into chlorines. This is going to be exciting. Then this molecule is going to have a dipole moment acting this way, one acting this way. They will sum into a net dipole moment acting in that direction. But if I were to look at, in fact, even better, if I were to rotate this all the way around, that's even better. I'm going to rotate this all the way around. So I'm going to end up with this arrangement. Right? So I'll keep this carbon stationary. So I'll have H prime and H double prime. And I'm going to rotate this until the Cl goes back into the board, then on top, back into the board, down, and then forward into the plane of the board. And I'm going to end up with this arrangement. Right? And what's going to happen is the HC will be behind the board, and HB will be up and in front. And while this molecule is going to have a net dipole moment, this one is going to have the two dipoles cancelled. So this is going to have a dipole moment of 0. So these two species, as with these two species, they have the same constitution, but they're not the same. So for example, the physical properties of these two compounds will differ. Right? The boiling points are different, the melting points are different, and so on. So these compounds are by definition isomers, but they don't differ in terms of constitution. They've got the same connectivity. So I'm going to call these stereoisomers, right? They're called stereoisomers. And in particular, I'm going to call these conformational isomers, right? I'm going to call them conformational isomers. So conformational isomers are isomers that have the same connectivity, but the position of the groups around the single bond differs. And I call each of these a conformational isomer of the other, or I call them different conformers of each other. Okay? And so the presence of the single bond allows free rotation about the bond, and free rotation allows the groups to tumble so that the spatial arrangement relative to each other can differ. That gives rise to a kind of isomerism called conformational isomerism. So because it's a single bond in alkanes, I can generate what's called conformational isomerism. Okay, so that doesn't look like conformational at all. This is conformational isomerism. So conformational isomerism. Well, what about alkenes? I mean, do we get isomerism in alkenes as well? And the answer is actually turns out yes. So if I look at an alkene, I've got a carbon-carbon double bond, right? That's what defines the vanillic center of an alkene. Suppose I do the same thing I did with the chlorines up top, right? And let's say I had the two chlorines here, and let's make these H's. And then let's put a chlorine here and a chlorine here, and let's make these H's. Now, how are these things related? Well, they've got the same constitution, right? I've got a Cl attached to a carbon attached to an H, right? Cl attached to a carbon attached to an H. That carbon is doubly bound to a carbon having a Cl and an H. That carbon is doubly bound to a carbon having a Cl and an H. So in terms of who is connected to whom, they've got exactly the same constitution. So these are not constitutional isomers. But it's not hard to tell that this compound is going to have a net polarity. So mu is going to be greater than 0. Whereas this one is going to have no dipole moment. Mu is equal to 0. So these are clearly then two different compounds. But what's interesting is the single bond allows you to rotate about it. And so I can interconvert this conformer into this one and then back again. In fact, there are pet names for these two. We call this one, and as I said, we will deal with this in more detail later on. We call this conformer, the one where these groups are bang smack in front of each other, we call this one the fully eclipsed conformer. Right? Or sometimes simply the eclipsed conformer. And this one we call the anti-conformer. Right? So what terms do we give to these? And they're related to eclipsed and anti, but they're not entirely the same. And the reason is, eclipsed and anti suggest not just a spatial arrangement of groups, but they suggest the fact that those things are interconvertible by rotation about the single bond. The problem is we can't rotate about the double bond. Rotation about the carbon-carbon double bond is impossible. It is forbidden. Rotation about any XY double bond is forbidden. So the question is, why? Well, one simple argument might be, well, because it's a double bond. Double bonds are stronger, so they lock things in place more tightly, and therefore things won't rotate. And as attractive as that might sound, it's dead wrong. Yes, you've got two bonds. Yes, things are held more tightly, but that is not the reason we don't rotate about the carbon-carbon double bond. The reason we don't rotate about a carbon-carbon or any XY double bond is really quite simple. And it has to do with the system wanting to maintain the integrity of the pi bond. So here I have an sp2 hybridized carbon bound to another one. And here I have a pi bond, right? This is my sigma bond, and this represents the pi bond. The pi bond requires side-on overlap of p orbitals. Remember, sigma bonds do not care which orbitals make them up. All sigma orbitals care. All sigma bonding requires is that the orbitals overlap end-on. Pi is much more specific. Pi requires p orbitals and that the p orbitals be side-on. And only when they're side-on could I get the overlap that defines the pi bond. So imagine now what would happen if I were to try to twist about this pi bond, right? If I try to twist about the pi bond, the p orbitals that make up the bond would lose overlap. If I lose the overlap, the bond vanishes. So that means I'm going to break the bond. That's problem number one. Problem number two is, should I succeed in breaking the bond, what would happen? And the answer is, I'm going to end up now with carbons only having a septet of electrons. Because the pi bond would disappear, I won't have my electrons being paired. So the carbons are going to have a septet of electrons, not the octet that they bargained for. And secondly, I would have unpaired my electrons and lost the magnetic attraction that stabilizes the electron pair. So it is to the advantage of the system to resist rotation about the double bond. We cannot rotate about a double bond. So what that means is, if the chlorines find themselves on the same side of the double bond, then they are stuck in that position. If the H's find themselves on the same side of the double bond, then they are stuck in that position. They cannot rotate out of it. If the chlorines or the H's find themselves on opposite sides of the double bond, then they are stuck in that position. They cannot rotate out of it. So I call this structure cis, and I call this structure trans. And I call this kind of isomerism cis-trans isomerism. I call it cis-trans isomerism, or I call it geometric isomerism. So it's called cis-trans isomerism or geometric isomerism. And that is a completely separate class from conformational isomerism. Because with conformers, the thing is, I can rotate from one conformer into the other. Now, this is a very important point to make here. The cis and trans compounds are unique. I can go to the store, I can go to Aldrich and order this compound. It's called cis-dichloroethene. If I order this compound, this is all I'll get in the bottle. I could order instead the trans-dichloroethene. And when I order that, this is what I'll get in the bottle, and only this. So these compounds are isomers. They are unique, and they are not interconvertible. So I can buy a pure sample of this and a pure sample of that. That is not the same scenario with these two, with the eclipsed and the anti-dichloro, 1,2-dichloroethanes. So if I go to the store and I try to buy 1,2-dichloroethane, that sample will contain billions of different kinds of molecules, billions of isomers. It will contain this one, and everything in between, all of them at once. It is not possible to isolate this compound from that one, because as soon as this one is generated, it starts to tumble about the single bond. So although these are different compounds and they are quite unique, they are interconvertible. And so it's not possible to freeze out one and isolate it. Once I have one, it will spontaneously convert into the other and back again, and to everything in between. So these are different, yes, but they are convertible species. I can convert one into the other by simple rotations. And by the way, rotations about a single bond occur 10 to the 12, 10 to the 13 times per second. They are very, very fast. And so it is impossible to generate one of these independent of the other. Unlike the scenario with the alkene, where I can get this one and it's frozen in the cis arrangement, the cis geometry, versus that one which is frozen in the trans geometry. So the presence of the carbon-carbon double bond does create isomerism, which is called geometric or cis-trans isomerism, right? Geometric or cis-trans isomerism. Well, what about the triple bond? Because we saw isomerism with the single bond and with the double bond. What about with the triple bond? And the answer is there actually is no isomerism with the triple bond. Which of course begs the point that it had nothing to do with the bonds being stronger, right? Why is this difficult? Right. So the triple bond, if you remember when we said that the carbon-carbon triple bond basically is like a cylinder of charge around the carbons. So what you might have is a scenario where you have different groups, let's say H and D or whatever, and they can rotate inside the cylinder freely. So much like if I take a pencil and I take a soda can and I punch holes in the top and bottom end, I can turn my pencil inside the cylinder and nothing happens, right? I mean, the line will turn, but it's indistinguishable, right? One turn doesn't make anything new, right? Because you want to imagine an atom as a faceless ball. And as I rotate that ball, if the ball has no marks in it, I cannot tell it's been rotated. And so even if I rotate it 10 degrees, 20 degrees, 30 degrees, I can't tell because the thing I rotated into looks exactly the thing I rotated it from. So isomerism is not possible in the carbon-carbon triple bond. So there's no isomerism here. So if a system is sp3 hybridized as an alkane, we can speak about the length of the bond and therefore the strength of the bond. And we can speak of the presence of the hybridization as being the genesis or not for different kinds of isomerism. Conformational in alkanes, geometric in alkenes. And of course, there's no isomerism in the alkyne. So notice now we have actually now met 3 different kinds of isomerism. We've met constitutional isomerism, right? As we saw, for example, with dimethyl ether and ethanol. We have met conformational isomerism, as occurs with single bonds. We have met geometric or cis-trans isomerism, as occurs with X double bonded to Y. I will make one point here about geometric isomerism, which is that I need to see, for geometric isomerism, that the difference between the 2 isomers. And what I mean by that is, I can have X double bond Y, but X must have 2 things on it. They don't all have to be atoms, right? But for example, if I had, say, C double bond O, and I had H, and I had D, and this O had a lone pair and a lone pair, well, if I switch the D's and the H into this structure, right, it's lone pair, I can't tell the difference one to the other. Because if I take this molecule and I turn it over 180 degrees, if I just flip the whole molecule over 180 degrees, good Lord, if I turn this over 180 degrees, it mirrors this one exactly. And I can't tell the difference between them. On the other hand, if I have C double bond N with an H and a lone pair, and I put H and D, that structure is different from this one. C double bond N with an H, a lone pair, a D, and an H, right? Because obviously if I tumble this molecule, it does not resemble this one. Or put another way, these H's are cis to each other, whereas here these H's are trans to each other, and they're trapped permanently in that arrangement. Okay? So in order for me to have geometric isomerism, the atoms must be doubly bound, and each atom must have 2 different things on it, right? They must have 2 different things on it. The things could be a lone pair and an atom, or there could be 2 different atoms. But each group, each atom in the bond must have 2 different groups on it, 2 different things on it. Okay, so that would finish the carbon-carbon scenario. The question is, what about the CH scenario? Well, it's not a big stretch to see what's going to happen with the length and the strength. So if you imagine, then we take our sp3 hybridized carbon, and for example, we marry it to the s orbital of a hydrogen. So here is the s orbital of a hydrogen. So the carbon-hydrogen bond is going to be that long. Here is the s orbital of a hydrogen. The carbon-hydrogen bond is going to be that long. Here's the s orbital of a hydrogen. The carbon-hydrogen bond is going to be that long. So what you notice is the CH bond shortens as I go from sp3 to sp2 to sp. And that is a result of the increasing s character, the increasing smallness of the hybrid. And while we're on it, if the bond is getting shorter, what that's going to mean is the bond length, as it decreases, it means the distance between the nuclei and the electron pairs is going to get shorter, and therefore the force of attraction is going to go up. Because if R goes down, F goes up. So as we said before, as bonds get shorter, bonds get stronger. So what I'd expect to see is that the sp3, is that the carbon-hydrogen bond for alkanes is the longest, and then it's not a stretch to say it is the weakest. The one for the alkene will be intermediate. The one for the alkyne would be the shortest bond, and then this would be the strongest bond. Okay? I'm going to change this term polarity into acidity because that's actually more in line with what I want to get to. So I'm going to talk about the acidity of the bond. Okay, so let's talk about for a second what we mean by acidity and what affects the acidity of an XH bond. So you'll remember from Gen Chem that if I look, for example, at let's look at a carbon-hydrogen bond. So carbon, then there's nitrogen, then there's oxygen, then there's fluorine. So I'm looking at atoms that are in the same period in the periodic table, right? Carbon, nitrogen, oxygen, fluorine. I'm going to look now at the halogens, right? The hydrides of the halogens. So this would be a chlorine-hydrogen bond, a bromine-hydrogen bond, and you can imagine then an iodine. I'm going to run out of room here. An iodine hydrogen. Well, let's just do the three of them because that's all the room I have. You notice I was careful to show that the length of the HF bond is the shortest, and that the HBr bond is the longest. And that's the simple fact that the Br is much bigger than the CF, which is much bigger than the F. Okay. As I go from carbon to F, the atoms do get smaller, but not significantly smaller, right? The difference in size is much greater down the group, right? However, the difference in electronegativity is much greater across the period, right? You guys remember that from Gen Chem, right? So I go from metals on the far left, which are strongly electropositive and weakly electronegative, to the halogens in the far right that are weakly electropositive but strongly electronegative. And I go from an atom, they're all in the second period, so the size might change from this big to that big as I go across the period, but I go from metal to non-metal, right? On the other hand, as I go down a group, I'm going from halogen to halogen to halogen. So yes, there's a slight change in electronegativity. It falls a little bit, but what changes markedly is the size. I'm going from fluorine to chlorine to bromine to the much bigger iodine. So going across a period, the change in electronegativity is much, much, much bigger than the change in size. But going down a group, the change in size is much, much, much bigger than the change in electronegativity. Okay? Now, how does this feature in our discussion of acidity of the CH bonds? Well, what happens as I go from an sp hybridized carbon? Oh, in fact, I actually had the diagram here. As I go from an sp hybridized carbon to sp2 to sp3, what you'll notice is two things. Going from sp to sp3, as the carbon's orbital gets smaller, the bond gets shorter. As the bond gets shorter, the bond should get stronger. Now, what do I want an acid to do? If I'm an acid, right? If I'm an acid, I'm HX, right? If I'm an acid HX, what do I want it to do? I want HX to break. I want both electrons in the HX bond to be dumped onto X to give me H plus and X minus. And of course, that's going to be an equilibrium. Inherent then in acidity is the breakage of the HX bond. What's also important is the stability of X minus, because the more stable X minus is, the more likely is the acid to form it. The more completely will the acid form it. So the more stable X minus is, the further to the right the equilibrium falls. So really then there are two things that seem to affect the strength of the acid, right? The lability of the bond, the stability of X minus. And you remember from your Gen Chem, X minus is called a conjugate base. Okay, great. Well, what makes the bond labile? And what do we mean by labile? We say a bond is labile if it is easily broken, right? So a labile bond is a weak bond. Okay. Whoa, man, that doesn't look like broken at all. So a labile bond is an easily broken bond. By the way, labile is an adjective that's used to describe both a bond, in terms of its weakness, and a molecule. So molecules are labile when they're reactive. And of course, reactive molecules tend to have weak or labile bonds. Okay? Let me amplify that a little bit. So I say if a bond is long and weak, it is going to be labile, right? And if a bond is long and weak, what that means is when I want to do a reaction, it doesn't cost me a lot of energy to break the bond. That means because remember the ascending portion of the plot is the energy I put in to break the bond. It's the reaction coordinate. So if the bond is labile, I don't put in a lot of energy, and therefore the activation energy barrier is small, the reaction goes quickly, and the molecule is reactive. So reactive molecules must not require the investment of massive amounts of energy to break the bonds. In other words, the bonds are weak. So labile molecules, reactive molecules, tend to have labile bonds, weak bonds. Okay? All right, so let me just go back up. So what I want an acid to do to express its acidity is to have the HX bond break to generate X minus. The more labile the HX bond is, the stronger the acid. The more stable X minus is, the stronger the acid. Now, another feature is I want the bond not just to break, but to break in such a fashion that X gobbles up both electrons. So the three things I want are a stable conjugate base to make the acid strong, a stable conjugate base, a labile bond, and I want X to be electronegative, because the more electronegative X is, the more it pulls, the more it sucks these two electrons towards it, hastening, right, encouraging the cleavage of the HX bond, and ending up absconding with the two electrons. So all three things are important. I want X minus to be stable. I want X to be very good at sucking electrons towards itself, and I want the bond to be weak. Great. As I go from alkane through alkene to alkyne, the CH bond gets stronger. And if that were the only factor, I would expect the alkane to be the weakest acid, because the bond is the longest and therefore weakest, and the alkyne to be the strongest, to be the weakest acid, because the carbon-hydrogen bond is the strongest. But that only speaks to the lability of the bond. But what about the electronegativity of X? Well, let's see. So the CH bond, the electrons are going to be shared somewhere here, right? This is where the overlap of the orbitals tend to occur. And as you notice, as we go from sp3 to sp2 to sp, the electron pair is going to drift closer and closer and closer to the carbon, right? The electron pair drifts closer and closer to the carbon as the carbon's orbital contracts, as it develops more and more s character. But we have a word that describes the ability of an atom in a covalent bond to suck electrons towards itself. And that word is electronegativity. So because the carbon, as it becomes more infused with s character, gets better at sucking the electron pair towards itself, we say that the electronegativity of an atom is not a constant. It depends upon the atom's hybridization state. And the more s character that the hybrid orbital has, the more electronegative is the atom. Which means this carbon is the most electronegative. And if it is, the dipole along this CH bond is the greatest. In other words, there's going to be like a delta minus minus, right? There'll be like a delta minus minus on the carbon here, and delta plus plus on this H. Whereas here, which is slightly longer, I'll have a delta minus and a delta plus. And functionally, for this carbon, there is no dipole, right? For this CH bond, there's no dipole. And so as we look from sp3 to sp2 to sp, the H becomes more proton-like, more protonic, and I would expect this to become more acidic. Now, I have two factors that are acting in opposition. One is about the length of the bond, which really is a size matter, the size of the carbon. And the other is about the polarity of the bond, right, which is an electronegativity matter. And you remember our argument. If we were moving across a period, electronegativity is the big matter. Okay? Well, if we're dealing with carbon, the change in size of carbon, right, carbon doesn't change whether it's sp hybridized, sp3, or sp2. The orbital gets slightly smaller, but what happens is there's a big change in electronegativity. So the electronegativity issue greatly outweighs the bond length issue. And as a result, the alkynes are actually the strongest acid because the CH bond is more polar and the H is more protonic. So alkanes are the weakest acid. Alkanes are the weakest acids, right? These are the weakest acids. These are intermediate, and alkynes are the strongest acids. Okay? Now, there's another point that needs to be made. So we are saying that what has to happen is that the XH bond has to break. We've identified that the bond has, the more labile the bond, the stronger the acid. And that would have suggested that the alkanes with the most labile CH bond would have been strongest acids. That turns out not to be borne out in practice because the electronegativity of the sp hybridized carbon is far greater. And the electronegativity difference creates a much larger dipole, and as a result, the alkynes are the strongest acid. So we've dealt with factors 1 and 2. But what about this third factor? So let's imagine then what would happen when the H comes off as H+, and we generate then the anion, right? The anions we generate are going to be, in the sp3 hybridized case, it's going to be this, for the sp3 hybridized case, this for the sp2, and this for the sp. So what does this mean? What this means is, this is the anion now, right? This is the C-. This is the conjugate base. What this means is that the swell of electron density in the anion from the alkane is actually kind of far from the nucleus, the carbon's nucleus. The swell of electron density in the conjugate base from the alkene, sp2, right? The swell of electron density in the alkene is closer to the nucleus. The swell of electron density in the anion, in the conjugate base of the alkyne, is even closer still. And what defines the stability of an electron is its proximity to the nucleus. This is why, when we look at our energy levels, the 1s is the most stable, followed by the 2s, then the 2p's, then the 3s, and so on, right? And why is the 1s the best seat in the house? Because the nucleus is here. So electrons in the 1s orbital are very close to the nucleus. And the force of attraction, the thing that stabilizes, is maximal when the electrons are close to the nucleus. The force of attraction is maximal when the electrons are close to the nucleus. And if the force of attraction is maximal, then we are most stable, right? If the bond strength is great, we are very stable. We've seen that in Morse curves. When I have a strong bond strength, the system releases a lot of energy. If I have a weak bond, the system releases less energy. This is a more stable scenario. So the conjugate base from the alkyne, which is called an acetylide, is by far more stable than the conjugate base from the alkene and the conjugate base from the alkane. And as a result, the alkynes are the strongest acids because the conjugate base is the most stable. Okay? So we can speak of the acidity of the alkanes, alkenes, alkynes, both in terms of the, well, really in terms of the hybridization states of the carbon, and the consequences of those in terms of the lengths of the bond, which actually work in opposition to us, the polarity of the bond, which helps us, and the stability of the conjugate base. Okay? So this gives us a profile then of the hydrocarbons and the impact of the hybridization states of the carbons on certain properties of the carbon-carbon bond and of the carbon-hydrogen bond. Okay, so we'll do two more things and then we'll stop. And we're going to look at the properties, the molecular orbital properties of a carbon-carbon double bond. And this is actually pretty straightforward. New page. So, if I'm forming an alkene, I'll have a carbon that's sp2 hybridized, and another carbon that's sp2 hybridized. They will each have a p orbital. So I'm going to have end-on overlap between sp2 hybrids, which will give a sigma bond, and I'll have side-on overlap of p orbitals, which will give rise to a pi bond. But you remember, as we did for the hydrogen, when two orbitals interact, we give a bonding and an anti-bonding. Right? So when the s's overlapped, I got a sigma 1s because it was end-on overlap, and I got a sigma star 1s. If I put in two orbitals, I get two orbitals out. Well, in this scenario, I'm putting in four orbitals, right? 1, 2, 3, 4. Two of them, the sp2s, are going to form sigma bonds. So they will form a sigma and a sigma star. Two of them will form a pi bond. So they will form a pi and a pi star. So what do these things look like? Well, we're not that much interested in what they look like, although I will draw a picture of it in a second. I'm much more interested in the energetics. So I'll start off by drawing what the orbitals look like. So when the sp2s overlap, I'm going to get a sigma sp2. I'm going to sigma sp2, which will look something like this. That's my sigma sp2. And I'll get a sigma star sp2, which will look something like that. Right, so this is the sigma star, and this is my sigma, right, my sp2s. What do my pi's look like? Well, I'll get a pi, which people draw differently. Some people draw it like this. Some people draw it like this, right? In which case, these are homophasic, right? So this is plus, plus, and minus, minus. And then for here, I'd have had like a minus, a plus, and a minus. And then here a minus, a plus, a minus, and a plus. So either one of these would be the pi. The pi star would look like this. And most people draw it the same way. The pi star would look like this. Right? So plus, minus, plus, minus. That is my pi star. So two p's, two pi's, pi and pi star. Two sp2s, two sigmas, and a sigma star. And the question is, what are the relative energies? And the answer is the following. Come on. The answer is the following. So the pi's are going to be flanked by the sigmas. So I'll have a sigma, a pi star, and a sigma star. In many ways, and I often ask classes if they've ever heard the rhyme about the little girl with curls. And almost in every class I've had, nobody's heard the rhyme. So I'm gonna teach you a nursery rhyme. And it goes, there was a little girl with curls. When she was good, she was very, very good. When she was bad, she was very, very bad. Sigma orbitals are like little girls with curls. When they overlap, so end-on overlap, right, allows the orbitals to get really intimate with each other. When they're overlapping in phase, that is really good and they get very stable, right? So when they're overlapping in phase, because of the intimate contact, I get really great stability. So the energy content is very low, right, in a sigma. But imagine if that intimate contact was occurring when the orbitals were out of phase. That would be horrible. So when the overlap is homophasic, the stability is great. When the overlap is heterophasic, the instability is great. And so the sigma is very low, the sigma star is very, very high. But when the p orbitals overlap, they're not overlapping end-on. I mean, they're barely reaching over to interact. So we get interaction, but it's not the kind of intimate contact that you get with a sigma. So when they occur in phase, it's good, but it's not great. And so the stability is kind of good, but it's not as great as a sigma. Similarly, when the overlap is out of phase, it's bad, but it's not as bad as the sigma star, right? So the pi star is higher than the pi, but not as bad as the pi star. So what we find is that the sigmas flank the pi's. Now, in an alkene, there are two bonds between the carbons. One is sigma. I don't know which one is sigma, which is pi, but one is sigma and one is pi. How many electrons are in the sigma orbital? 2. Where do they go? They'll go in the sigma orbital. How many orbitals in the pi bond? 2. Where will they go? They will go here. So what is the order of the carbon-carbon bond? Well, I have 2 bond pairs minus 0 bond pairs. So my bond order is 2 minus 0, which is 2. So whoop-de-doo, it's a double bond. Right? What do I call these orbitals? Well, I'll call this one my highest occupied molecular orbital. And I'll call this one my lowest unoccupied molecular orbital. Right? Pi star is my LUMO. Pi is my HOMO. What do I call this one? I'll call it my HOMO minus 1. Or I can call it my LOMO, which is my lowest occupied molecular orbital. What do I call this? I call it my LUMO plus 1. Right? Or I can call it my HUMO, my highest unoccupied molecular orbital. So the HOMO and the LUMO together are referred to as the frontier orbitals. They're called the frontier orbitals. Okay? So the HOMO-LUMO pair are called the frontier orbitals. And all the other orbitals are named relative to the HOMO and LUMO. So they'll always be HOMO minus something, right? So for example, you can imagine a scenario where I have something like this. Oh, come on. Something like this. So if I have, bang, 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 and I might have electrons here and here, and here, and maybe here, I'll call this HOMO, I'll call that LUMO. I will call this LUMO plus 1, and I'll call this LUMO plus 2, which I can also call HUMO. I'll call this HOMO minus 1, HOMO minus 2, HOMO minus 3, or LOMO. Right? So once I identify my frontier orbitals, the HOMO-LUMO pair, I name everybody else relative to it. Everybody above the LUMO is LUMO plus something, right? The station removed from the LUMO. Everybody below the HOMO is called HOMO minus something. The station, removed from the HOMO. Okay. So I'll make one little point again about geometric isomerism, which is, and I sort of made the point, but I'm going to amplify it. In order to get geometric isomerism, then, I need to have 2 different groups on each of the vinylic carbons, and we'll deal with alkenes. I need to have A, B, and it could be A, B, or B, C, or C, B, or whatever, it doesn't matter. In order to have geometric isomerism, I must have different things on each carbon. Okay? Because if I had, so if for example I would have moved, let's say I would have B, C, and A, B. These are different because here the 2 B's assist to each other. Here they're trans. Here the A and the C assist to each other. Here they are trans. But if I have this arrangement where I have AA and say CB, if I flip those, right? If I flip those and I have BC, these 2 molecules are exactly the same. They're just rotated. So if I take this molecule and I turn it over about this axis 180 degrees, I get that molecule. Right? And you are the same whether you're standing, sitting, running, or lying down. If I change the molecule's orientation, that doesn't change the molecule. So to get geometric isomerism, I must have different groups on each of the 2 carbons. Okay? So geometric isomerism is possible only when there are different groups on each carbon. I will remind you that if I had a compound like this, H and D, I would have geometric isomerism because D and H are isotopes and they're not identical. Okay? So isomerism is possible here, but not, for example, in that molecule. Right? So isomerism possible here, but not here. Okay, so that would be the end of the early part of Module 2, and we'll pick up from here next day. Thank you.